So good morning class, welcome to today's session. We are going to do a recap of instruction set. This is a follow-up of what I discovered from your colleagues. So few of them approached me with a question paper of of programming. Actually, the question was about programming, and I was surprised that actually they were not able to interpret the table which we are provided at the back of the question paper. So the reason why we have this session is to interpret those instruction set, group them into instructions category, and later on we are going to solve some few problem. So you are supposed to cover these objectives at the end of this session. So first of all, we are supposed to interpret instruction set provided by NEC. We are supposed to group them into key categories, and then we are going to solve some problem using instruction provided by NEC, so that we are going to see how do we apply that knowledge. So at the back of the question paper of microprocessor systems and microcontroller technology, you realize that we have this weird table. At first it looks weird, but I want to tell you that this is a very important instruction set which we are going to use to build our programs as we solve problems with 8085. Remember, I told you that 8085 is like any other IC, but this IC you can program, you can change how it functions. The other IC which are hardwired, you can only use them in the system which they are programmed to work in that environment. It means that you cannot actually program them to do different tasks apart from what they were specifically designed to do when they were manufactured. So for example, 555 timer, it's an IC, but this IC, the work of this IC is to generate an output which oscillates between on and off. The only thing you can do is to either increase the frequency or reduce the frequency using the passive components. But microprocessor, Intel 8085, you can program it. It means that you can program that IC to do different tasks. Now, since we can program Intel 8085, we have what is called instruction sets. Instruction sets, these are special codes. Let's say these are just special codes, and these codes are used by the microprocessor to govern how it carry out its tasks. For example, we can program we can instruct the Intel 8085 to perform addition of numbers. We can instruct it to transfer data from one memory to another. We can instruct it to perform arithmetic operation, among other things which we are going to see. So those codes which we normally use to instruct the Intel 8085 are called instruction set. So the instruction set are normally called mnemonics when it comes to Intel 8085. Yeah, imekuwa grouped into what is called, the basic structure is the mnemonics. So remember, the instruction set ikona what is called the opcode, and then we have what is called the operand. The opcode is the instruction itself, the operand is the data which the instruction is working on. Now, as you know, opcodes, these are machine codes, and they are normally written in hexadecimal. So these are found on the left side of the instruction codes which are given in 8085. So this is the NEC, a sample of NEC past paper. At the back, you will have this table. So in this table, we have the opcode here, and then we have the mnemonic. The mnemonic is the instruction which as human beings are able to write or even to interpret. the machine or the microprocessor will have to interpret this instruction. And how does it interpret the instruction? It changes to what is called opcode, and opcode are written in what? Hexadecimal number. So these are just hexadecimal number. So anytime we write an instruction, that instruction is interpreted by the Intel 885 to an opcode version. These are like hexadecimal numbers. For example, we have a mnemonic code which is an NOP. So if you look at the opcode version of it, it's what? 00. So you go 01, 02, 03. For example, we have another one, MVI L, D8. So this one is an instruction which is mnemonic. The opcode version is what? 2E. The opcode version is 2E. So if you are told that you've been given an instruction, come up with the opcode, so you go to where that instruction is located. For example, if you've been given move E, C is an example of instruction whereby we are moving data from C to register E. So this instruction, the equivalent opcode version, it's this number. So that's how we normally use this table. So we have the mnemonic and we have the opcode. I've said the opcode is what the machine will translate or will interpret the instruction. The mnemonic here is how you or any other human being is able to write what? The instruction. Remember, if you are supposed to write instruction using the opcode, it's very difficult. But it's much easier writing using what? The mnemonic. But you are going to see that it's much even easier to write using what? Higher level programming languages. So now the mnemonics, these are assembly language instructions. These are beside them. So beside them, these are assembly language instruction. So we have the machine language instruction, and then we have the assembly language instruction. Of course, we don't have the higher programming language instruction. Those are like C, C++, Java, Python. So as I was saying, the instruction set at the back of the paper, it's categorized in opcode and mnemonic. So for example, I have a mnemonic here whereby I'm loading register BC as a pair with a memory address, which is actually a 16-bit address. So this one is a type of mnemonic code which is going to perform that function. The equivalent opcode is what? OA. Remember, this is an hexadecimal number. We have another one of incrementing C. So this instruction increment register C by 1. So what is inside register C is going to be incremented by 1 when you execute this instruction. The equivalent opcode version is OC, which is an hexadecimal number. So why do we have this opcode and mnemonic? Mnemonic is how human being can easily write instructions or programs which can be executed by the microprocessor. But microprocessor is not able to execute these instructions the way it is. So it has to translate this instruction to opcode. Opcode is like hexadecimal number. It's not like an hexadecimal number, it's actually an hexadecimal number. So anytime you have this instruction, when the microprocessor fetches this instruction, it will interpret by translating it to what? Opcode, which is equivalent to 02H, which is an hexadecimal number. Another one is this one. You are loading or moving immediately a data which is 8-bit to register C. So this one is MVIC D8. The equivalent opcode is what? OE. So that's how you use that instruction, or that's how you interpret the instruction which you are given at the back of the paper. So let us now look at what is the meaning of D8. Why do we have some dashes in some section? So that's what we are going to do next. So another thing which you'll notice at the back of the paper, you have been given some writings at below the table. And these writings, first of all, you find something like D8, D16, ADR, or sometimes even M. Now, D8, it means that if you have an instruction, let's say you have an instruction like MVI D8. So MVI C D8. So this is an example of an instruction. So this instruction is going to load an 8-bit data, any 8-bit data, to what? To register C. D16 means we are going to load an 16-bit data to register pair. Remember, we cannot hold 16-bit data in one register because one register carries 8-bit data. So if you want to store 16-bit data to a register, you have to pair two of them. So you can pair H and L or B and C. So the most common is H and L. So if you have an instruction and that instruction contains ADR, it means that you are loading a 16-bit address to the register. So we normally use this one when we want to jump to a certain instruction, or we want to call an instruction from a certain address. And then dash, for example here, this one is undefined, and it means that that opcode has been reserved. We don't have an instruction equivalent of that opcode. So this one we've covered several times. I told you that all instructions are grouped. So anytime you see an instruction, you have to recall, what does this instruction perform? The function of that instruction is you can categorize those instructions based on what they perform. For example, we have instructions which they transfer data. So they copy and move data. So for example, MOV, MVI, LXI, LDA, STA, LDAX, STAX, LHD, LHLD, SHLD, XCHG. Okay, let me talk about few of them, so you know these are now familiar with you. This one is when you want to load an immediate data to accumulator. So you want to load an 8-bit data to the accumulator, so you use what? LXI. This one is when you want to load data from the memory location to the accumulator. This one you want to store data from the accumulator to a memory location. This is when you want to load register pair with a 16-bit data. Okay. Somehow it's funny. This is when you want to store data from a register pair. This one you want to hold. Yeah. This one when you want to load data to register pair HL. This is when you want to store data from register pair HL to a memory location. So let us go back here. This one you want to store data, you want to load data from the memory location to the accumulator. This one here is when you want to load data from the register pair to the accumulator. This is when you want to store data from the accumulator to the register pair. This is when you want to load data from the memory location to register pair HL. This one you want to store data from register pair HL to a memory location, and this is when you want to exchange data. Hey, now, okay, remember when we have a 16-bit data, we have to use this instruction. Yeah, they are very complicated. And then we have arithmetic instructions. I told you these are addition. This one is what you add and what you carry. This one you subtract. You subtract with the carry. Increment, you decrement. Yeah? Increment register pair, decrement register pair. So now you realize when you see X, it means that you are dealing with 16-bit data, and you are supposed to use register pair when you are dealing with what 16-bit data. And then so the story continues. So we have logical instructions. These are NA. So this is you AND a register with what is inside the accumulator. You OR a register with what is inside the accumulator. Yes. This is XOR of what is inside the register with what is inside the accumulator. For example, you can say X R A, comma B. So here you are XOR. So you are XOR what is inside register B with what is inside register, with what is inside the accumulator. Branching, these are instructions which will enable you to jump between the instructions. So you can jump to a certain instruction if something occurs. This is most of the time when we are executing a loop. You can call a subroutine, a small instruction to handle an interrupt. You can reset your instruction using RST. I mean, you can prioritize the interrupts. Remember, we have the interrupts RST 5.5, 6.5. So you can call one of the interrupt using the RST. RET is to reset, and then we have some conditional jumps. Jump if zero, jump if carry, jump if no carry, etc. So we have also the control instructions. These are like out. This is when you are sending data to an output port. This is when you are enabling another microcontroller using an enable signal. This is when you want to stop the instruction. Yeah, this is when you want to stop instruction for one line, among other things. Actually, we've discussed these things, gentlemen and ladies, in our classes. So this is just a recap. So the next thing I want us to look at, I want us to see how can we use those instructions to solve some problem. So let's say you've been given a task of copying the contents of register B to A. Yeah, so you're supposed to copy the contents of register B to A. So which instruction are you going to use? Move to register A, which is our accumulator. What are you moving there? What is found inside what? Register B. So let's say if register B contains a data which is 8 as a decimal number. So if you convert 8 as a decimal number to binary, I think it's equivalent to something like 1, 1, 1. So you add some 5 zeros. So it will become 0, 0, 0, 0, 1, 1, 1. So this one which is inside register B is going to be moved to the what? To register A, which is our accumulator. Remember, when you execute this instruction, it's not going to delete what is inside register B. That's just going to copy. So that's the solution is going to be move A, B. Explanation, the content of register B is transferred to A without altering B. So you can also be given another task, load 25H into accumulator. So 25H is a number which you are supposed to load to the accumulator, which is our register A. So remember, this is a number which is not stored anywhere. So this number is just found inside the instruction, or it's just found inside your mind. So we normally use what is called immediate instruction. So immediate instruction, these are instructions which normally ends with what? I. They normally end with I. So if you see something like ADI, MPI, those are examples of what? Immediate instructions. So for example, this one, I'm going to load data which is 25H into what? Accumulator. So this is remember, this is a 8-bit data, so it's much easier to be handled by the accumulator. So explanation, moves the content constant value 25H directly into A. Immediate data means the value is part of the instruction itself. So you can also be given a problem for you to add two numbers which are stored in different memory location or registers. So for example, here we are supposed to add the contents of register B and what? C, and store the results in A. Now it means that after executing this addition of the two numbers which are found in register B and C, then you just leave the answer inside A. So here, first of all, I can decide to move either what is inside B iende kwa A, or what is inside C iende kwa A, and then later we'll add the one which is the remaining one. So if I move B to A, then I will have to add C to A. If I start with C to A, then I will have to add B to A. For example, here I decided to move what is inside B to go to what? A. So copy B to A, and then later on I add what? C. So what is going to be inside A is going to be A plus C. And what was inside A, which we transferred what was inside B earlier. Now you are noticing something. This semicolon, I told you that when you put semicolon, that is the end of that instruction. It's like a full stop. You are telling the computer this instruction stops here. We go to another instruction. We go to another instruction. And then when you want to stop the program, you use what is called what? Halt. 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 So you stop the instruction. You stop the program. Full stop, which is our semicolon here, tells the microprocessor this is the end of the instruction. So whatever you are going to add after that semicolon cannot be executed. So you can add your code explanation. For example, here, copy B to A. This one is just a code explanation and cannot be executed. Always write your instruction and remember to put what? Their comments, some explanation. So the accumulator always holds one of the operands, that is true, and the results of an arithmetic operation. So first of all, we have to move B to A, and then add C, and then what is going to be inside A now is going to be the results. And actually we tutakuwa tumeachieve hii goal, store the results in A. So you can also be told to subtract E from D, store the results in accumulator again. So remember here again, one of the data must be moved to the accumulator. And for example here, because we are doing the subtraction and we are subtracting E from D, we have to start by moving D to the what? To the accumulator. So move A, D. So you are moving what is inside D to the accumulator, and then subtract E. So we are subtracting what is inside the accumulator with what is inside the register E. So subtract the sub instruction subtract the operand from A and store the results in A. So this is another one. So if we are supposed to add two 8-bit numbers from memory location, so we have one stored in memory location 2050H and another one in memory location 2051H, and our final results should be stored to 2052H. So we will start by first of all loading what is inside memory location 2050H to the accumulator, and then later on we'll add what is inside memory location 2050H to accumulator, and then we'll store the results from our accumulator to memory location 2052H. So we LDA, so load accumulator with what is inside memory location 2050H, move what is inside the accumulator to register B. Why are we executing this instruction? We are executing this instruction because we need our accumulator to be free for it to receive what? The next data. So remember, our next data here is going to be transferred from this memory location. So we load first of all what is inside 50H to the accumulator, and then we transfer what is inside the accumulator to B. Then we load the next memory location, which is 2051H, to the accumulator. We add what is inside the accumulator with what was inside B, and then later on store the results to memory location 2052H, and then we stop what? The instruction. So here remember, we are using the registers because referring back to the memory location, it's far from the microprocessor. Remember, memory is not part of the microprocessor, it's an external device. So if we are supposed to be working from the memory, it will be much slower. So we better move those data to the register. And that's why you saw the first thing we load the instruction, we load the data from 2050 to the accumulator. Then we transferred that from the accumulator and register B to make the accumulator available for the next data. And then now, after loading the new data from 2051H to the accumulator, we now add what is inside the memory. What is inside register B. And then now we store our final results now from the accumulator to the memory location 2052H. So you can also be told to increment value. So for example, here we have 5FH. So this is 5F, which is an hexadecimal number. It's found inside memory location 3000H. So we are supposed to increment this value by 1. So remember, this is a 16-bit data. You need more than 8-bit binaries to represent this number. So whenever you need more than 8 binary bits to represent a number, that number falls under what? A 16-bit. Because the next number of bits you are going to require are 16-bit. Remember, you cannot say you only need 9 bits. No. We go by what? 8, 8, 8, 8. So you'll need what? 16 bits. And that's why we say this is what? A 16-bit number, or 5H hexadecimal number. Now, because it's a 16-bit data, we are supposed always to hold that data using what? A register pair. And here we are going to have a register pair H and L. So LXI H. So we are loading what is inside 3000H inside the register pair HL, where 5 will go to H, F will go to L. And then we are going to increment memory. So what is being held by the register pair, which is our memory location address, we are going to increment what is inside here by 1. and then we are going to halt the program. So we have another one. This one is a little bit difficult. So let's say we are told that we are supposed to add the first 10 natural numbers 1 to 10. So you can have a long way to approach this if you cannot have a shortcut. So if you decide to have to go a long way, then you will be doing, maybe you will say you will move 1 to register A or B, and then later on you are going to add 1, you add 1, you add 1 up to 10. That can be a long way to go. Now what are you supposed to do now? Remember again here, the instruction is telling you that the task you are supposed to complete by storing the results to memory location 50H. 2050H. Now, how can you approach this? A good approach is for you to have a way of counting. So when you add 1 plus 1, for example, if you add, for example, 0 plus 1, you will get 1. You store this 1 somewhere, and then you have a counter which is going to count 1. So it means that you are supposed to count up to 10 for you to finish that addition of 10 natural numbers, or 1 to 10 natural numbers. Now, if you are supposed to use the counter, then you can store the number of count, and the number of count here is 10. So 0AH is an hexadecimal number which represent what? 10. So 0A, you are going to load this data immediately to register C. So this is a data which is not found anywhere, so you are going to use immediate instruction. So you move 0A, which is an hexadecimal number, to memory location C. Now that one is going to be our count. You need somewhere where you are going to store what? Your summation. Now we are going to use register B, and register B, because we've not done any summation, it's going to hold 0 0, because at the beginning our sum is going to be 0. So 0 0 hexadecimal number. Now inside our accumulator we are going to load our first natural number, which is 01H. So we load our accumulator with our first natural number 01H. So up to this level, I want us to understand what have we achieved so far. Now we've decided that register C is going to hold our count number. Register B is going to hold our summation. Register A is where we are going to do our addition. And the first number which we are going to load to this register A, which is accumulator, is 1, which is 01H in hexadecimal. So that's our current number. Now we are going to enter into the loop mode. And the only way we are going to escape this loop mode, so we are going to enter this loop mode here, and the only way we are going to escape this loop mode is after a certain parameter has been met. We are going to see what is that parameter. So the loop is, we are going to start this loop by adding B. So what is inside register B is going to be added to accumulator. So it is 0 plus what is inside the accumulator, which is 1. So it's 0 plus 1, which is going to be 1. We move that 1 again from the accumulator back to the register B. So our register B, which is holding our sum, is now going to contain what? 1. We increment now. We go back to our accumulator. Accumulator is going to contain 1. We increment it by what? 1. So it's going to go to 2. And then we decrement what? C. What is inside C? Our counter, which is 10. So we decrement, it remains 9. we repeat the above. We come again to B. So we add what is inside B, which is 1, with what is inside the accumulator, which is 2. Remember, we incremented it to 2, so the result is going to be 3. We move that 3 to what? To the register B, and then we increment accumulator from 2 to 3, and then we decrement register C from 9 to 8, and then we repeat again that way. So we are going to stick inside this loop until a miracle happens. What is that miracle? Until our counter is decremented from 10 to 0. When we reach 0, now we will escape this loop, and we are going to move our final data, which is going to be inside A, to register B. And and after we escape that loop, we are going to move the final summation, which is inside register B, to the accumulator, from register B to the accumulator. Yeah, it's very funny here. Yeah? So you enter into a loop mode, you repeat the task until something saves you from that loop mode. And here, the only thing is going to save us to escape this loop is when our counter is decremented to 0. Then we are going to move what is inside B, which is what? Our summation, which is going to be equivalent to the number which we are going to get if we add 1 to 10. So the final thing, we are going to store that data from the accumulator to memory location 2050H, and then we stop the program. So ladies and gentlemen, that comes the end of our session. This session was very much important to you because you are supposed to know how to use the table, the instruction table, which you are provided at the back of the question paper, to build your instructions. And if you are given a problem, and how are you supposed to approach that problem using the instructions which you have been given. So remember, this reference sheet is provided for students taking microprocessor systems to assist them in compiling and recalling instructions more easily during examinations and laboratory sessions. So don't make it difficult for you to remember all the instructions. Those instructions are provided at the back of the question paper. So it serves as a quick access guide to the Intel 8080 or 8085 instruction set, summarizing all opcodes, mnemonics, and their classifications into major functional groups such as data transfer, arithmetic, logical, branching, and control operations. Now that marks the end of this session. Please find time to watch this video. It's very, very important. And also try to go through the instruction sets at the back of the question paper to see if you can recall them. Enjoy your day. We are going to meet on Thursday for a physical class. But for now, please let this help you.